On the YouTube, I see an error occurred. Hello, welcome. I'm Ed Pegg Jr., and welcome to my talk on covering sets. I'll be discussing many items dealing with how to cover aspects of certain setup problems. Martin Gardner wrote a column called Mathematical Games for Scientific American for 25 years, and it was a highly influential column. And this series of episodes hopes to cover some of the things he did in those columns and the 15 books that came out of them. One item that Martin Gardner did quite a few times were problems involving covering sets. One of the problems is one of the features of covering sets is that they work in many different ways. For example, there's many demonstrations we have that cover covering sets, including sparse rulers, the Mondrian art problem, substitution tilings, the Klein configuration, gray codes, and I hope to cover some of those, de Bruijn sequences. So one item in the news recently related to covering sets is, can you cover a tetrahedron so it is stable on only one face? And that's a question that was recently solved. This is a link to a piece on, I can't remember where it is, but I've got a link to it there. Oh, I should probably be able to see it. Anyways, this tetrahedron is only stable on one face. It's based on Hep's two-tip tetrahedron, which can be seen here. The center of mass is at the dot, and there's only two faces that are stable on this shape. And some people figured out that you could add weights to this tetrahedron and make it only stable on one face. Another item in the news is the Kuban triangle problem, which is something that Martin Gardner discussed. He wanted to know what the maximum coverage of non-overlapping triangles is for a given number of lines. For example, with 5 lines, you can make 5 triangles. With 7 lines, you could make this many triangles, and so on. And he wondered how that sequence would proceed. And there are some answers published in his column for 10 lines. And now we're up to 31 lines as of yesterday. So yes, yesterday on Wednesday, this solution was announced for 31 lines, and it meets the maximum, so it's the best possible solution. And there's I believe I've posted, you can go to the community post to see what these links are if you'd like to follow any of them. And also, always feel free to ask questions in the link. Another type of covering is to cover a shape with identical copies of another shape. For example, the circle covering problem, which was a frequent item in carnivals. You'd have to cover a circle with 5 discs. Unfortunately, the solution is somewhat strange, so you have to be careful about how you're placing things when you're trying to solve it. And this is a demonstration on the demonstration site if you want to try some of these covering problems. They can be quite tricky, and if you go to Eric's Packing Center, you can find what the solutions are. So I'm not quite doing this. I don't think I've covered all the orange. Oh, maybe that does work. So this is a little bit off. I see some orange down here, but it is possible to solve this problem. This is called Spot the Spot in Gardner's books. For 12 circles, we get this particular arrangement, which was found by this guy, and it uses a particular root. And that root also solves the Heilbronn problem for 12 points. And this is how to cover a square with 12 points so that the smallest triangle that's formed by those points is as large as possible. And that's the Heilbronn problem. And it turns out for 12 points, you use the same root as for 12 disks covering a circle. So that's sort of unusual that the same root is used for two different problems. This root is also seen in a strange algebraic problem. You basically want a polynomial whose coefficients are equal to the roots of that polynomial. So minus 1.77 and so on, 0.565, 0.639. Well, if it turns out if you have a polynomial with those coefficients, the roots are the same thing, minus 1.77 and so on. I can't quite scroll down quite far enough to see what the root is there, but you can visit the community post if you want to look at what the actual roots are. And this strange value here, minus 2 minus 2a plus a to the third equals 0. That same root is closely associated with e to the pi times the square root of 19. And you can see it here. We get this almost integer here. And when we compare it to e to the pi squared of 19, we get a very similar number. So there's 4 different strange coverings all involved with the same algebraic number. Another famous covering problem is the weighing problem. You have 4 weights and you want to be able to, and you've got a set of scales and you want to be able to weigh everything from 1 to 40 grams. And if you use the ternary system with weights 1, 3, 9, and 27, you can do that weighing. And this is known as the balanced ternary system, which is actually more efficient than the binary system because it's closer to Euler's constant E. So it could make slightly better computers. Unfortunately, it's hard to do 3 parts in a circuit rather than 2 parts if for binary. So the binary system won out, even though mathematically the balanced ternary system is slightly superior. Another covering problem Gardner did several times was using squares to cover things or to divide a square into smaller squares. One question he wondered was, can you cover the plane with consecutive squares? So here's a triad. He's got the squares from 1 to 11, but you can't fill in that space. And you've got 3/4 of the plane covered with consecutive squares here. Well, it turns out there is a solution for this, the Ponting square packing. So we can see it better with smaller numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14, 15, 16, 17, 18, 19, and so on up to 25. You can do a square number of square tiles with this particular shape. And the matrix for these, oops, let's try a smaller number. Here's how the matrix works. You've got the numbers 1 to 9 at the bottom, and then 10 to 17. On the gray checkerboards, they just keep going up to half of 17 squared. And then the alternate numbers start here, 146, 147, they go down this way. And if you look at these cross sections, 1 plus 162 is equal to 153 plus 10. So all these lines indicate where there's two sets of squares next to bordering each other. So going back, we can basically use any number of squares and cover the plane with those squares. We just need to pick a sufficiently large square number. Gardner also would like to talk about chess covering problems. One of his favorites that he used 3 times, placed 5 white queens and 3 black queens on a 5x5 chessboard so that they don't attack each other. The solution for that is unique. I don't show it here because it's a very good puzzle. Another question he did was, how many queens can you put on a board so that each one only attacks one other queen? And here's the solution for the 9x9 board, which happens to be unique. You can put 12 queens on a 9x9 board so that each one only attacks one other. He also covered the problem of sparse rulers. This is in his Dr. Matrix book. And the question he has here is by Leach, John Leach, the same person who invented the Leach lattice. He wanted to know how you could put 8 marks on a yardstick of 36 inches so that it could still measure all distances from 1 to 36. And here's the solution for that. This is the Leach yardstick. You start with a space of 1, then a space of 2, a space of 3, 3 spaces of 7, 2 spaces of 4, and then a final space of 1. And that's the unique way of making a yardstick with 8 internal marks. The ending points of the yardstick are considered free for this problem. It turns out there's also a unique 1 meter ruler. This will measure all distances from 1 to 100 here, starting with 2 1s, a 3, 3 5s, 6 11s, 2 6s, and then 2 more 1s at the end. This problem of sparse rulers was an open problem for a long time, and it turns out that I was able to solve it without too much difficulty. Basically, I started with a construction by Brian Wickman and figured out that if I extended it, I could get all sparse rulers above a length of 1 million automatically. So basically, for large values, the problem was already solved back in the 1960s by Brian Wickman. But there were smaller values that were a lot trickier. And that's what I spent almost a year of computer time on a small laptop, working on covering all these smaller values. Here's another ruler, which I call the 1 meter ruler, which happens to have a space of 1 meter. And this will measure up to 214 centimeters. If you have a nylon tape, it's easy to make these markings. And notice the simplicity. It's a bunch of 1s, 100, 4 3s, 10 8s, and then 3 5s. These simple sparse rulers that only have 5 different types of gaps run out before a length of 300. Everything past that requires at least 6 different lengths. With Brian Wickman's construction, I figured out that all rulers needed this many marks. So if you had a length of n equals 100, it would be 3 times 100 plus 9/4, square root of that, and plus either 0 or 1. It turns out for this 1 meter ruler that you need exactly whatever the square root of 300 is, rounded. You need that many marks for this ruler. And when I started making stacks of the excess values, the 0 or 1 values, I noticed this pattern. You get this dark area here, and you get these values up here. And when I extended this problem to 10,000, I got this strange pattern, which MJ Sloan, who runs the online and encyclopedia of integer sequences, he called this pattern dark satanic nulls on a cloudy day. And that name is stuck for this pattern. Part of the solution was finding a lot of different ruler constructions like the Bryan-Wickman construction. And I found about 800 different constructions, which you can see in this demonstration here. And there's also a demonstration on sparse rulers where for any distance, you get what the marks are, and you get the coverage of values which meet that, the gaps between marks that meet that, shown automatically. And I wrote up the sparse ruler problem at our blog item, hitting all the marks, which you can take a look at. So for this item here, you can see that all lengths up to 50 are covered. For example, here's the coverage for 13 here. Here's the coverage for 34 here. So that's another type of covering problem is sparse rulers. That is basically a length on a straight line. We can also do lengths on a circle. And those give cyclic sum sets, which were discussed by Singer in 1938. And here's a section from his paper. For example, we've got partitions of 7, 1, 2, and 4, or marks on a circle with a circumference of 7. We put those marks at 0, 1, and 3. So the distance of 2 can be measured by the difference between the marks at 1 and 3, and a difference of 3 between 0 and 3, and a difference of 4, since the total circumference is 7, is also 0 to 3, but going the other way, because 7 minus 3 is 4. And these are different markings for different sets, basically modulus 21 for this case. You could do 16 minus 0 and 0 minus 16, mod 21, which is 5. And the partitions are the distances between them. So if we do cyclic sums, for example, 5 plus 1 is 6, 2 plus 5 is 7. I'm sure there's a way to do 8. 10 minus, or sorry, I'm sure there's a way to do 8, and I'll show it later. With a Singer difference set, there are this many terms for a prime power q, such as any prime number 3, 5, 7, or any power of a prime, such as 2, 4, 8, 16, 32. Q is a prime power, and for example, 2 to the 14 would be 2 to the 4 plus 1. For 2 to the 4 here, there are 17 terms, and the modulus is the number squared, which would be 16 in that case. So in this case, it's 16 squared plus 16 plus 1 for the 2 to the 4 case. And there are this many different variants of that particular construction. So I have a demo in the works that builds all of these Singer different sets and cyclic sum sets shown here. And many of these have variants. For example, with this particular value here, there's 78 variants. So you can go into this demonstration and see the different sets that are generated. For 21, there's only a unique different set for it. Now this is a perfect different set, or a perfect cyclic sum set. Every single value from 1 to 21, there is a unique way of adding up wedges on the outside to add up to that value. For example, if there's only one way of getting to 9, 3 plus 1 plus 5. It turns out there's one more unique partition, and that is at 28. As a puzzle, try to come up with a dissection of 28 into 6 terms. And the helper is it's not perfect because there's repetitions. There are repetitions for multiples of 7 when you work on 28. And with that information, that's enough information for you to deduce what the partition is for 28 into 6 terms. So let's try a few others here. So these are the different cyclic sum sets for 31, 57. Now, one of the odd things about powers is notice that this is for 2 to the 3rd, basically. So it's a powers of 2 item, and this particular solution starts out with powers of 2, 1, 2, 4, 8, 16. It turns out that the next block of items here adds up to 32, and then the remainder of 10. The same sort of thing happens here. We start out with powers of 2. This next block equals 64, and the next block equals 128, which I thought was unusual. But there's also many variants of each of these. So those are particular Steiner constructions. We can ask, and here's a further item here. These are the same cyclic sum sets, but this time I'm showing where the arcs are. I need to combine these two, and these arcs in the middle here show where these particular values are. We can ask for cyclic partitions for any n value. And so I started looking at this. There's a solution for 28. Don't look at it for too long. Once you get to higher values, these get very difficult to find. I just recently got these solutions for 109 and 111 yesterday. I forgot to add them here. But this is unsolved how this sequence continues. We know that, I know now that this is a 12 and 109 is 12. We still haven't figured out these values, but how this pattern compares to the sparse ruler pattern is still unknown. It's unknown whether these values are actually 2 or whether this whole thing as it continues to infinity is just 0s and 1s. Due to the difficulty in constructions, I don't think we'll know the answer to that anytime soon. We can also use different sets to make odd pictures of how things combine together. For example, here's how to use the 0, 1, 4, 14, 16 mod 21 different set. And if we add 1 to all of these, that gives another equivalent different set, and we can keep adding values from 1 to 20 and get different sets. And they're all shown here in circles of various sizes, circles or lines. They're all arranged here. Same thing happens with this different set, 0, 1, 3, 9. If we add 1 to that, we get a equivalent different set. So for example, where is 0 here? Oh, 13. There should be 0. 13 is equal to 0. So 0, 1, 3, 9. There should also be a 1, 2, 4, 10. So 1, 2, 4, 10. Any two items are connected by a unique parabola in this second construction. If we continue with those, that's how the game of Spot It works. Any two cards in the Spot It set will have a unique item in common. Similar to these, if you take any two parabolas, they will intersect at exactly one item. And same with any two circles here will intersect with just one item. If we set these as cards, for example, these two cards will share one value, which happens to be 44. And the same happens with larger values. We can do the same thing with the 43 set. And the object of the game spot is to be the first to spot what the match is. And I'm terrible at this game. 38 is what matches on this. And we can continue to say a 133 set, which has 12 items on each card. A different sort of covering that Martin Gardner covered was polygon dissections, where you cut up one polygon to make another polygon. How can you get the same set of shapes to cover both polygons? This is the number of pieces known. Recently, it was proven that the square and the triangle need exactly 4 pieces. The rest of these haven't been proven as optimal, but these are the current records as they are currently known. I did a whole talk about these on polygon dissections. Similarly, for our 16th episode, I covered space-filling curves and covered some of these curves here. In the 17th episode, I covered combinatorial codes and designs, which is a big topic. One of the items one of the most famous of the codes is the Golay code. And this is the entire paper by Marcel Golay. This is a kind of a revolutionary paper here, even though the code he came up with was for the ternary code was found 2 years earlier by some people who did cricket betting. There was a newsletter that had this same code in the optimal way on betting on cricket matches in 1947. We can generate the Golay code in many ways, and one of the ways is to use the icosahedron. And if you basically join up the edge list of a icosahedron with diagonals, as shown here, we get a basis for the Golay code. So basically all combinations of these 12 rows. There's 4 other very interesting ways of generating the Golay code that I know of, and there's probably many more. In the 19th episode, I talked about Turing machines. So basically, if we cover all programs, what do order n simple programs do? And so far, that's only solved up to 7, at least for the busy beaver problem. These are some of the pictures that came out of that study. The busy beaver for order 6 was recently solved. They're not sure whether order 7 is solvable because it uses a collat sequence. I also covered covering sets in my talk, the 26th talk, Puzzles on a Square Get Rid. One of those is the Mondrian art problem. We want to divide up a square. In this case, a square of size 138 into rectangles of different size, integer size, so that the smallest rectangle and the largest rectangle are as close to each other as possible. So in here, I believe the smallest rectangle is 178 and the largest is 1200. So these aren't too different. They have a total difference of 22, and it's very difficult to come up with anything that beats it. This is, in fact, believed to be the best solution. And in this, I've got many different best known solutions, but this is only solved up to about, I think the latest is up to square size 70. But these solutions that I've posted are pretty hard to beat. I say that, but I had this published before the records came out up to 70, and many of my solutions from 50 to 70 were off by 1. So I didn't find the best solutions, but it still took a lot of effort to beat the solutions I posted. One of the Cayley problems from Steiner systems is the Kirkman schoolgirl problem. You have 15 ladies in a school walking 3 abreast for 7 days in succession. You need to arrange them so that no 2 walk twice abreast in that week. And Cayley was the one who solved it using dominoes in this grid. So for the first day, you can read out the solution. The ladies in this case are the numbers 1 to 8 and the letters A to G. So for the first day, ABC is in one set of 3. D35 is another set of 3. E17, F28, and G46 are the 15 young ladies. And if you keep going through that way, ADE, B26, C48, F15, and G37, that's the next day. And this covers all 7 days where all 15 of them walk 3 abreast for 7 days in succession with no 2 sharing a column on any more than 1 day. So this method that Cayley used, this is now called a room square, where you have all the pairs up to a given order so that all numbers appear in every row and column. But Room was a mathematician. He wasn't born yet. This particular solution introduced the matrix into mathematics. He called this a matrix. He started doing other math with it. And since then, we've got linear algebra. We can solve this problem another way. So here's another solution, and we can put the solution in this way. All of the pairs in here have a binary XOR of 0. And this is a way of arranging those values so that every item is on an arc or a straight line. If we look at just 1, 2, 3, 4, 5, 6, 7, that happens to make a Fano plane in gray. And this is what's known as the smallest projective space. Expanding this up, we can look for more complicated problems, and those are known as social golfer problems, which are notoriously difficult to solve. And this demonstration here has many different solutions for the social golfer problem. It looks like I'll need to adapt this to fit better. And these are known as resolvable Steiner triple systems. Another thing Steiner is known for is Steiner trees. And those are easy to get. We basically put nails on a board. These blue points would be nails, and we dip those into soap water. And the soap film that occurs puts 120-degree angles at particular points, and that is the minimal road coverage connecting those 4 towns. So it's possible to set these up so that these are solved automatically, and those we can add more points. And that is the Steiner soap film Steiner tree solution for road optimization. And that's the best way of covering a set of roads given a set of particular locations. However, it doesn't account for terrain, and when they build roads, they take terrain into account. Another Steiner system, for example, 239, can be built out of magic squares. So if we take the low shoe magic square and we pair it up with just the numbers 1 to 9 in order, any 2 values are in a row or column uniquely. For example, 1, 2 is unique. They're not in the same row or column over here. 2, 3 are in a different row and column here, and so on. Any 2 items that are in a row or column here are not in a row or column over here. And we get this particular pattern for the low shoe as a Steiner triple system. We can expand that with another puzzle. You want to make a magic square here so that anything that is in the same row, column, or diagonal here is not in a row, column, or diagonal here. And it turns out that every possible pair from 1 to 16 will be in one of these 2 squares. And here's a method for solving where the first value would be. We know that 9 and 4 won't be in the same row. So the only values you can put here are these values, 6, 14, and 15. Also, we want a value here, which is on the main diagonals over here for balance. So the value 6 has to go here, and that means 15 has to be here. We can then arrange everything to make this pattern where every possible pair is on a line or circle arc. This can extend to a magic hexagon, and there we add toroidal diagonals as well. In one direction, though. So we can see what the hexagonal grid is, and it's better presented with a clipped hexagon like this. The 5x5 case uses toroidal diagonals in one direction. The 7x7 case uses toroidal diagonals in both directions. So here we can look at all the this still has all the values 1 to 49 in order, and the puzzle would be to finish out a 7x7 magic square over here. And it's possible to solve this with pure logic. And the value 1 here is completely given. Venn diagrams can do coverage. So here's code for doing a Venn diagram purely as identical polygons shown here. This is a order 5 Venn diagram. And here's another way of doing it here, which I think is a nice, pleasing pattern. Graceful graphs also do covering. For example, this one here, all these edges have all values from 1 to 12, and there are exactly 12 edges, and the edges are the differences between the vertices. For example, 12 is between the vertices labeled 0 and 12. 7 is on the edge between 2 and 9, and 9 minus 2 is 7. Gardner did a column about graceful graphs, and there are various unsolved questions in that. One way you can build graceful graphs is to just put in any permutation. For example, I'll just make up a permutation. I'll just do 14, 13, 13. That is a permutation. And that gives this particular graph. One question is, and these are based on a Lamer codes. Here is the Lamer code for this same permutation up here. You notice that the Lamer code has a bunch of zeros, ones, twos, and sixes in it, and the 4 of the vertices are 0, 1, 2, and 6. And there's a reason for that. One question you might ask is, what are the smallest graceful graphs with a particular valence? And it turns out you can do that if you use sparse rulers, which I talked about earlier. Since I happen to have solutions for sparse rulers up to, well, it was a proof by construction. I have builds for all sparse rulers up to infinity, and there's code at the function repository. You can put in any value, and it'll give you a sparse ruler for that value. Google and Googleplex, anything. If you happen to know a particular length you need, you can look at my database of sparse rulers, which is complete up to 213. It's a link for it is back in the sparse ruler section. You can use those sparse rulers to construct graceful graphs. And that's what I did with these. These are the smallest graceful graphs with a particular valence. For valence 9, it gets rather messy, but you can take a look at the graph complement, and it's almost planar. And I continued on. There's a post I did that has larger graceful graphs of a particular valence. We can use the value around the square root of 3n plus 9/4 if the number of edges is that the minimal number of vertices is given by n being the number of edges here. So if it's more compact than that, it's impossible to make a graceful graph out of it. A de Bruijn sequence is a way of cyclically covering all combinations. For example, 0001 is here, and somewhere here 0001 is the next. Somewhere here will be 0011. Going cyclically, all binary combinations up to 1111 are covered by a de Bruijn sequence. And it was an open question for a while whether you could extend de Bruijn sequences to 2 dimensions. And it turns out you can. And I have a demonstration which shows some of the known de Bruijn sequences for given sizes. Another type of covering is to take something and then to split it up into identical copies of something smaller. For example, with the 24 cell, you can split it up into 3 hypercubes, as shown here. The 3 hypercubes in blue, green, and red. Similarly, the complete graph K16 can be covered with 3 copies of hypercubes with diagonals, which is also known as the Club's graph. You can see it more clearly with this one. It's not obvious that these are hypercubes with diagonals. So this basically proves that the Ramsey value for 16 is greater than 16. The Ramsey value for 3 coloring with triangles is greater than 16 because this is a way of 3 coloring K16 so that there are no triangles anywhere. one game that Gardner liked was two coloring connections in a hexagon, and the first to make a triangle loses. It's possible to do all but one edge of a complete map of the hexagon so that it's still a tie game, and that's a nice puzzle. We can also look at covering space with polyhedra. The most complex way to do that is to use the angle polyhedron, and here it is surrounded by 38 copies of itself. The angle polyhedron having 38 sides. And here's a picture of the angle polyhedron. It's sort of hard to see, but there's a whole bunch of small sides on the edges here. But you can reflect these around to get a complete coverage. It turns out that each of these tiny pieces has an identical tiny piece elsewhere on the figure, so that you never use mirror images when you cover itself, when it covers itself. And this is a space-filling polyhedron. We can also ask, what is the minimal number of coordinates that can be used to cover a polyhedron? So for example, the icosahedron, you only need signed permutations of this coordinate. So you just need one, and that generates all 12 vertices of the icosahedron. All of these Platonic and Archimedean solids just need one coordinate, and all of these just need two coordinates, and then it gets more complicated. But with just a few coordinates, you can get all of the Platonic and Archimedean solids. Another covering is to cover all the vertices, and that's known as a Hamiltonian tour. So we can take a polyhedron and come up with a Hamiltonian tour which covers all the vertices. One unsolved problem: can we cover every row and column of a grid with two markers so that there are never three markers in a straight line? Well, it is possible to do that with 52. You can put 104 points in a 52 by 52 square so that there's never 3 points in a straight line anywhere. But this is the largest known for this particular problem, and this has been unbeaten for, I think, 1990s was when this was found. So over 30 years, no one has been able to come up with a better solution than this. Orthoschemes are another form of covering. You have a tetrahedron, and it happens to make a larger copy of itself. With 8 copies of itself, it can completely cover a twice larger version. There's only 5 different tetrahedra that can fill space, and so far as I know, there's only these 2 tetrahedra that can make larger copies of themselves. Here's the other one here. And for a long time, I wondered what happens with a full tiling? What happens if you keep going? And I finally coded that up. It wasn't too hard. Here's what order 2 looks like for the first orthoscheme here. And here's what the second one looks like for the second orthoscheme. This one looks much more regular. So that's a way of using one tetrahedra to cover a 4 times larger version of itself. There's 64 of these tetrahedron in this figure. We can also wonder how we can cover all different orientations of a die while it's rolling around. And I did that experiment with an octahedron, and you get this particular item. So for example, the octahedron has 8 faces, and it turns out while it's rolling, one point of that can be in 3 different orientations. So there's a total of 24 orientations. And here's a map of all of them on a torus. And it turns out this is equivalent to the Nauru graph, also called now the rolling octahedron graph. This is the same graph as positions of a 2 by 2 by 2 Rubik's cube with only half twists and one cube kept fixed. You also get the Nauru graph. The icosahedron is more complicated. It has 120 different orientations, but you can get them all by doing this particular rolling in a triangular grid. And you get what's called the Foster graph 120b. A similar problem is to use a cube to get all 24 orientations. And that's a nice little puzzle, seeing if you can get a map for the 24 orientations of a cube rolling within a small space. Another type of covering is magic squares of various sorts. So here are all the tuples from -8 to 8 that sum to 0. And it turns out you can arrange those on disks so that they're always in a straight line. For example, 1 plus 3 minus 4 is 0. And it turns out that all of these sums are somewhere in this grid. -7, -1, 8 is in a straight line. We can do that with -7 to 7 as well. And here are all the various lines. There's a lot more lines in this one. And it turns out that this is a solution to the orchard problem that happens to be sporadic. The most lines you can get for a 3 in a row problem is here. 1, 6, p minus 3, p, 4 plus 1. There's only 4 values of p known that can hit this extreme upper bound or lower bound. And here are the solutions here. So here's the 16 case, but this is also a solution up here with these green lines, faint green lines. There's 6 faint green lines connecting to a point of infinity. There's 15 points here, a 16th point at affinity. So this is a sporadic solution that Terence Tao happened to miss. These are all 4 sporadic solutions of the orchard planting problem. One question I asked is, how can you cover a vertex with similar triangles? And it wasn't too hard to write code to find all of these. So this is a demonstration power wheel graphs. An unsolved problem is how to do this with tetrahedra. And I still don't know the answer to that. How can a similar tetrahedra cover a single point in 3D space? One item recently found was whether oscillators for all periods could be done in the game of life. And that recently got solved in 2023. It turns out there's a complete coverage of oscillators for all periods in the game of life. We can also look at a graph, the coordination sequence, the number of vertices at distance 0, 1, 2, and so on. So for example, for this graph, the coordination sequence is that for all vertices. Usually, the coordination sequence for a particular vertex is not the same as another vertex. But these are examples of graphs where the coordination sequence for all vertices happens to be the same. So we have a lot of graphs that have coordination sequence 1, 3, 6, 4 for all vertices. But there's also many cases, for example, 1, 3, 6, where the graph seems to be unique. So this is a open question. How can you find a graph with a particular coordination sequence for all vertices? And one last item, which I thought vaguely fit covering, was the 7 cylinders problem. Let's see if this will work here. You want to put 7 cylinders so that they all touch each other. And here's a solution. This wasn't solved until about 10 years ago, I think. The Gardner would have really liked this. So the talk is at the community site. In fact, I've got a link for that here. This link will be on the YouTube discussion. And many thanks for attending my talk. If anybody has any questions, I'll be glad to answer anything. Just feel free to post any questions you might have. And I'll see if I can answer them. So I suppose I can close it there. Many thanks for attending my talk.